Howdy team, welcome to the second video in our first exploration into the data structure called trees. Now we're going to talk about a cool example of binary trees that's used in um, compression, but also it can be kind of a mysterious way to send a message to another person. So you could call it a very easy to break um, encryption as well. Okay, so we're talking about Huffman trees. This is a really cool data structure where we are able to represent a series of binary values, so zeros and ones, and we can use those zeros and ones to represent different characters, so like A, B, C, D, whatever. But a Huffman code can compress that information instead of using 8 bits or 16 bits or however many bits it is in your operating system to store a specific character, we can reduce that to 3 bits to 4 bits. And that can make it it can make sure that you are using less memory or less bits to encode even complex information. So ASCII and Unicode, as I just mentioned, they used a fixed number of bits for each character. So you know that each character, I'm going to move on 8 bits, move on 8 bits, move on 8 bits. That's not necessary when you are using a Huffman encoded message or a text string. So here's an example of a Huffman code tree. You could arrange this tree in any way that you like. This is just one example of such a tree. And in this tree, it is trying to um, add, it is trying to make sure that the shortest paths are going to be representative of the letters that you'll use the most. So in this case, the code for E is going to be right here. Um, Let me draw that, and maybe I will switch to red to be easier to see. So E is right here. And we can see that E is the only leaf at its level. So if you're talking about the levels of the tree, we have one here, we have one here, we have one here, we have one here. Um, E is the only leaf at that level, and it is the first level that has a leaf. So E is going to be the letter that has the fewest bits to represent it. So the way a Huffman code works is we have a series of zeros and ones. Zeros means a zero means travel left, while a one means travel right. So to get to E that I've already pointed out is right here, we have the code 010. So that means we need to travel left, then we need to travel right, then we need to travel left again. So if we see 010, we will know that that represents an E. Let's find another letter. We have an S, which is going to be 0011. So if you think about that, that means that we are going to go 0 means we go left, 0 means we go left, 1 means right, and we go right another time. So let's trace that. We are going to go left, and then left, and then right, and then right, and look, we have found S, which is pretty cool the way it's able to do that. The code for B and the code for W, you can see that these ones are a little bit farther away. Or they're farther away. We can tell that because they have more bits required. And those far bits are going to mean that we use these characters a lot less often. So let's trace B and where we will find that. It says 1. 1 is the first digit, so we're going to go right first, and then we go left 5 times. 1, 2, 3, 4, 5. And look, there is B. You can follow a similar process for W. And then here you can see these are the farthest away, and that means that these are the letters that are going to be used the least frequently and will have a um, longer number of bits to represent them. So I want you to take a second and figure out, oh, why not Q? Can you find the Huffman code for the letter Q? All right, I hope that you paused the video. If you haven't, please do so now. And let's talk about it. So we need to find Q. So we need to start by going right. That means we have a 1. And then it looks like we need to go right again. So we have another 1. And then we go left 0. We go left again for 0. We go left again, which gives us another 0. And left again, which gives us another 0. And then we go right, which gives us a 1. And then we go left again 2 times, 2 more 0s, and then a 1 gives us Q. So this is the value for Q. You can see how that is much longer than the code for E. Okay, so next, I want you to pause the video again when you write out the code for a word this time. This time the word rakes. Pause the video, come back when you have it done. Okay, you're back. I'm here. Let's go through at least a couple of the letters. So first we need to find the R in rakes. The R is right here. So we need to go left. That's 0. We're going to go, that gets us here. We need to go left again, which gets us here. And then we need to go right, which gets us here. And then we need to go left again, which gets us to R. So 0010 represents R. Now we need to find A. Where is A? A is going to be here. So let's add some binary for that. So we need to go, we start here, we go right. So we have a 1, and then we need to go left, which gives us 0. We need to go right, which gives us a 1, and we need to go left again. So this is A. Now we need to find the I, which is where? Here. Okay, so we start out at the root. We go left, which gives us a 0. Then we go right, which gives us a 1. We go right again, which gives us another 1. And then we go left. This gives us I. Let's do one more letter. We'll do the K because we've already done E and S. So let's do the K, which should be probably longer. Yeah, it's all the way over here. So we start at the root. Of course, we go right, which gets us here. It looks like we need to go right again. And then we go left to here. We need to go left again to get here. Left again, left again, and then right 2 times to get K. So here is the letter K. You will also have added E and S to this. Um, okay, now I want to show you how, so long as you have the tree, and even if you don't have these sections that determine which letters, like where a letter starts and stops, you're still able to decode the message. So let's start decoding this with we'll just start decoding with the bits. So we know we have a 0, we need to go left, and then we need to go left again, and then we need to go right, and then we need to go left. We found a character, so our message has an R in it, and we have read that many characters. Now, once we have found a letter or a character, then we start again at the root. So this time we go right because of a 1, and then we have a 0, and then we have a 1, and then a 0. So now we have an A, and we know that there is a character separation there. Then we're going to start over one more time. I think giving 3 examples will be enough. We start at the root again. This time we go left for a 0. We go right 2 times, and then we go left 1 time. That gives us an I. So even if we don't have any like bit sequence that represents a separation of numbers or a separation of characters, excuse me, we do know that we can move on to the next character, that we start again at the top of the tree. Okay, so I hope that is a fun example of binary trees. I hope you can encode messages now to your best friends and do it in fewer bits than you otherwise would. Um, is sort of fun. Okay, so in the next video, we're going to be talking traversals, and I'll see you then.